I'm Jeroen van Meij and welcome to my lecture series on computer and network security. In this third video on secure network protocols, I will continue with TLS and SSL and focus on attacks that exist against these protocols. And I will mainly talk about two vulnerabilities against SSL and TLS. And the first one is Heartbleed. Heartbleed, the name may ring a bell, is often called the internet's worst vulnerability to date. And it's actually not a problem with TLS or SSL itself, but in the OpenSSL 1.0.1 implementation of this protocol. OpenSSL is the most widely used implementation of TLS on web servers. And in March 2012, a minor programming error was introduced into this implementation of OpenSSL. It was only publicly made available in April 2014, so that means the vulnerability existed for 2 years before it was discovered and may have been abused by attackers in that period. When it was discovered, still 17% of the internet's secure web servers, so these are the web servers that were using HTTPS, were vulnerable to the attack. That means over 500,000 servers. And the attack was based on one line in the OpenSSL implementation, namely a copying of an array into another array based on the size of the payload of the data in the heartbeat message of the heartbeat protocol of SSL. So how does the attack work? Well, if the payload array, PL, is smaller than what payload size states, old data in memory allotted to the BP array will not be overwritten. The goal here is to copy the data in the payload array of the payload size into the BP array and then send back the data that's in the BP array. This is what the heartbeat protocol of TLS states you should do. But if the payload array is shorter than what payload size states, then BP array will not be fully overwritten and there's still data in memory located to BP array that is not overwritten and will be sent back to the receiver, in this case an attacker. And let's look at a concrete example to make it more clear. So in the heartbeat protocol of TLS, a client will send a short message to the server, for example, in this example, the word bird. And it will say, here is a word of 4 letters, please respond. The server will put that word in memory, transfer it to another array, and then send back the data. So that's the PL and the BP arrays. So the server responds also with the word bird, which is also 4 letters. However, due to this bug, the client could say, server, please send me this 500-letter word, bird, back. The server would not check if the word sent by the client was actually 500 letters, it's only 4 letters, will put the word bird into the array BP, but this array also contains a lot of other data from memory that was not overwritten, and will send back 500-letter word containing bird and a bunch of other information. This other information could be sensitive information such as session keys, master keys, data sent by other users, and so on. So this vulnerability had a potentially very high impact, as attackers could obtain information stored in the memory of web servers. And a lot of web servers were using this OpenSSL implementation. Here, for your information, you can see the fix to the problem. It's only a few lines of code, and they fixed the heartbleed bug. So it's basically 2 checks that check whether the heartbeat is not 0 characters long, and to make sure that the length that was provided by the client is actually the real length of the heartbeat message. The second attack I would like to talk about is the Poodle or padding oracle on downgraded legacy encryption attack. It relies on the fact that SSL version 3.0 is used in compatibility mode between the client and the server. You may wonder which web server still uses this old version of SSL, as in the meantime, a lot of new versions such as TLS 1.0, TLS 1.1, and TLS 1.2 have been introduced. Well, it is because a lot of web servers still offer these older versions of SSL for backwards compatibility reasons. So the attack consists of two stages. First, the attacker will act as a man in the middle and trick the server into reverting to this old version of SSL 3.0. And second, the attacker will actually perform the Poodle attack. So how does a man in the middle trick the server into using an old version of SSL? Well, the attacker can control the network between the client and the server and intercept any handshake messages where the client offers to use a newer version, such as TLS1 or newer. If the attacker intercepts these messages, the client will retry with older versions, thinking the server does not support these newer versions. When the client then finally offers to use SSL version 3.0, the attacker will not interfere and allow the negotiation to finish. As such, they will downgrade both the client and the server to use SSL 3.0. The padding oracle attack relies on a few characteristics of SSL version 3. First of all, it relies on the fact that SSL version 3 uses cipher block chaining, where each block of plaintext is XORed with a previous ciphertext block before encryption. It also relies on the fact that the attacker can find out whether a given ciphertext produces plaintext with valid padding. It doesn't need to know whether the plaintext itself is correct, but just whether or not the padding is valid. This is enough to break the CBC encryption. An often used type of padding with SSL is PKCS7, where each padded byte equals the length of the padding. For example, if a block is 13 bytes long, then 3 bytes will be added to create a full 16-byte block, where each padded byte is actually the length of the padding, so 3. So a 13-byte block is padded with 3 bytes that all equal the number 3. A 14-byte block with 2 bytes that all equal the number 2, and a 15-byte block with 1 byte that equals the number 1. That means, in this case, valid padding just means that the last n bytes all have the value n. And here you can see how this actually looks in practice, and also that the attacker will try to determine the intermediary decryption state. So that means the state before the decrypted ciphertext block is XORed with the previous ciphertext block. Because by retrieving this intermediary decryption state and knowing the previous ciphertext block, which is not so hard when eavesdropping on a network, the plaintext P2 can be retrieved. And let's take a closer look at how an attacker could exploit this procedure to obtain the intermediary state I2 of a ciphertext block C2. The attacker can make use of the fact that many web servers, when sent a piece of ciphertext, will actually give an error if the padding is incorrect. So the attacker can look at this error that is returned to know that the padding is not correct. So the attacker can send a short message to the web server which contains the ciphertext block C2 that they want to decrypt, combined with some cleverly created ciphertext block C1-. C1- is created by the attacker and can be initialized to some random bytes. However, the attacker will set the last byte to the value 00. Then C1- and C2 are sent to the web server, and the web server will try to decrypt this very short message consisting of 2 blocks. Since C2 is the last block in this message, the web server will check whether or not C2 contains valid padding. The padding is valid, as I mentioned, if the last n bytes of C2, of the decrypted block C2 equal n. Obviously, the probability is the highest that the last byte equals 01. The probability is much higher than the last 2 bytes equaling 0202 or the last 3 bytes 030303 and so on. So, if the padding is not correct, the attacker can just increase the value of the last byte of C1- by 1. So instead of using 00, the byte 01 is used instead, and the message is sent again to the server. Once correct padding is found, the probability is very high that the intermediary state, that the last byte of P2- is 01. So from this, the last byte of the intermediary state of C2 can be derived. Namely, the last byte of the intermediary state of C2 is the last byte of C1- XORed with P2, the last byte of P2-, which we know with high probability to be 01. And from this also the last byte of the actual plaintext block P2 can be derived by XORing the last byte of the actual previous plaintext block, ciphertext block C1 that we did not use in the attack before, with the last byte of the intermediary block I2. So in this way, a single byte, namely the last byte of a ciphertext block C2, can be derived. Now this process can be repeated to derive the previous to last byte as well. We already know the real last byte of the intermediary state I2, and now we want to force the padding of the last 2 bytes of the decrypted message P2- to be 0202. So we make sure that the last byte of C1- now will ensure decryption of the last byte to 02 by setting the value to 02 XORed with I2, with the last byte of I2, which we already found out in the previous step. Now we will repeat the process by iterating over all possible values for the previous to last byte of C1-. This will be repeated over and over, starting with value 0, 1, 2, and so on, until P2- has correct padding. Now we know for sure that, since we know for sure that the last byte was set to 02, that the padding is 0202. So we now know that the previous to last byte of P2- equals 02. And in the same procedure as before, we can derive the previous to last byte of the intermediary state I2. And from that we can calculate, using the original C1 block, the second to last byte of the plaintext block P2. This can be repeated over and over again to derive more and more bytes until all the bytes of C2 of the plaintext block P2 associated with C2 have been discovered. And that is how the padding oracle attack works. To make sure everyone understands, I have a question for you, where you can try to run the poodle attack to discover the last plaintext byte of a block C2. So given is the last byte of the previous block C1, which equals the hexadecimal value 24. Now the poodle attack is being performed, and the attacker discovers that the padding is correct when setting the last byte of C1- to the hexadecimal value 94. My question to you is, what is the actual value of the last byte of P2? the plaintext block associated with the ciphertext block C2. This question also ends my lectures on SSL and TLS. In the next video, I will talk about SSH, another protocol for secure communication across the internet.